Welcome back. I see you've come back for more. Let's talk about the second lesson here, atomic structure. And we are going to talk a bit about this. And so fireworks, I love watching fireworks, but if you've seen enough firework displays, you notice the same colors over and over again. You see the same types of reds, you see the same types of purples, the same types of blues. And that has to do with chemistry, and we'll talk about that through the lesson. So let's talk about the atoms. We talked about Dalton's atom last time. He thought that all atoms of the same element were alike and that different atoms of different elements were different. And he also thought they were spherical. They were like balls in a playpen. Turns out that he's wrong, and the more correct answer is the nuclear atom from Rutherford. And there's more. There's also the plum pudding model and various things, but I'm not going to go through all of it, but I like some of these just because they tell stories. And so right now we have the atom having a small, dense center called the nucleus, and then electrons on the outside called the electron cloud. So atoms are really, really small. Really, really, really small. So 1 times 10 to the minus 8 centimeter or 1 times 10 to the minus 10 meters. Really, really small. So tiny that it is impossible to see them with just light that our eyes work off of visible light. We can image them using STM, scanning tunneling microscopes. So we can see them, and it's in quotation marks. You don't see them with light, we see them with imaging. And here is an STM image. This is an STM image of graphite. So your pencil lead, this is what it looks like with a scanning tunneling microscope. And with atoms are made of smaller things called subatomic particles, and atoms are made of protons, neutrons, and electrons. Protons and neutrons are found in the nucleus. Electrons are found primarily outside of the nucleus. Electrons can be in the nucleus, but they typically do not spend as much time in the nucleus. They tend to spend more time in the electron cloud surrounding the nucleus. Protons have a positive charge and one mass of approximately 1 AMU, atomic mass unit. Same with neutrons, have no charge. They are slightly heavier, or more massive, I should say, than a proton, and they are also found in the nucleus. Electrons are about 1/2000th the mass of a proton or a neutron, and those are typically found outside of the nucleus. And we talked about Dalton, but let's talk about Rutherford. So Rutherford wanted to prove Dalton by using radiation, and this is the experimental setup, and I'll talk about what he meant. So he could take gold. You can hammer gold really, really thin. So really, really thin, and Rutherford took a alpha source. So a smoke detector at your home works the same way. It shoots out radiation, and then when smoke hits the radiation, it ionizes the smoke and then finds a detector. So Rutherford shot radiation at this piece of gold foil and put a phosphor screen around it, and then looked when a particle hits this screen, it flashes. And what Rutherford found out was, so I like this story because he forced his grad student to do all his work. So he told his grad student to go in this dark room and to take one of those clickers, like when you go into a club, and click every single time you saw a flash of light. And so the grad student did this for like 2 weeks or a month, sitting in a dark room, crouching down, writing things down. And he brought the data to Rutherford, and Rutherford expected atoms to be hard, solid spheres. He said, "This is not right. Go and do it again." The grad student did it again, got the same result. Brought it to Rutherford, and Rutherford said, "No, this is still not right. Do it again." The grad student was like, "Hey, look, you're doing your professorly things like drinking coffee and hanging out in your office while I'm here working really hard in the lab. This is the right data, or you can do it yourself." And so Rutherford thought, he said, that's probably right. And so this is what he came up with, is that the atoms are mostly empty space, but there's a really dense solid part. And this explained a lot of the data. So the empty space explained why most of the radiation went right through, but some was deflected in various angles, and that's been the positive center. And how dense is the center of the nucleus? Well, you can, from the previous slides you saw that it contains, about 2,000 times as much mass or more than the electron cloud. If you take a golf ball, so a little tiny golf ball, and you put it on the 50-yard line of the Aloha Stadium, or pretty much any other stadium for you mainland listeners, and you go to the nosebleed section seats, the golf ball is about the size of a nucleus, and the rest of the stadium is the size of the electron cloud. And we're going to classify elements by the number of protons. The atomic number is the number of protons. It defines the element. Carbon has 6 protons. If an element has 6 protons, it's carbon. If an element has 7 protons, it's nitrogen. Then the mass number for specific nuclei is, or I should say a specific nucleus, is the number of protons plus the number of neutrons. And we'll cover this a little bit more in depth later. So for the nuclear symbol, the top number is the mass number, number of protons plus the number of neutrons. The bottom number is the atomic number, number of protons. And the number of protons defines the element. And let's talk about isotopes. If you like The Simpsons, I like The Simpsons. The name of the baseball team is the Springfield Isotopes, and they have a nuclear power plant. So you might think that isotopes have something to do with nuclear events. And this is where Dalton was wrong. He said that every single atom of each element was the same. You can actually have atoms that are different. And these are atoms that have the same number of protons but different number of neutrons, and they're called isotopes. For instance, carbon has 4 common isotopes: carbon-12, carbon-13, carbon-14, and 14 is the mass number. Carbon has 6 protons, and so because of that, it has 12 minus 6, or 6 neutrons. Carbon-13 has 13 minus 6, or 7 neutrons. Carbon-14 has 14 mass number minus 6, the atomic number, 8 neutrons. Carbon-14 is also radioactive. We didn't talk about electrons. For an atom is neutral, so the number of protons equals the number of electrons. So atoms are electrically neutral. And here are 3 isotopes of hydrogen. There's protium. No one calls it protium except for chemistry teachers. Most everyone else calls it hydrogen. There's deuterium, also known as heavy hydrogen, and tritium, which is radioactive. Atomic mass, so when you look at the periodic table, which we'll look quite a bit, the bottom number on the periodic table is the atomic mass. That's the average terrestrial meaning on Earth. On Earth, there is the relative abundance of those isotopes, and it's averaged. So here, for iron, the weighted average there is the atomic mass. Now, another thing to note, atoms are the same throughout the cosmos. So if you take water here on Earth and you find water on Mars or the Moon, that water is the same. The hydrogen and oxygen in that water molecule, those elements are the same as the elements here. The same as the hydrogen, oxygen, water in some distant galaxy across the cosmos. The universe is made up of those 116 or 117 elements, and it's uniform across the cosmos. So what can be different, though, is this weighted average. On Earth, it is relatively uniform. Ionization, so atoms are neutral, but you can form ions. Ions are charged atoms, and that's an oxymoron. Oxymoron is when you have 2 things that are opposite. Charged means not neutral, and atom meaning neutral, so a charged neutral atom. And you can ionize atoms, and you ionize atoms by ripping off electrons. And the amount of energy it takes to rip an electron off is called the ionization energy. So when electrons are ripped off of an atom, a positive ion forms. An atom does not gain positive charges by gaining protons. By gaining protons, you will change the element. So ions are made by adding or subtracting electrons. And atoms, as they add electrons, they form anions, and negatively charged ions. So if you have trouble remembering between a cation and an anion, cation are positively charged. Think of the T in cation, C-A-T-I-O-N. The T, think of it as a plus sign. So anion does not have a T and it doesn't have a plus sign, so it's negative. Now, this shows a mini periodic table, and it shows you things that tend to, the charges that atoms tend to have. So lithium, sodium, potassium, iridium, cesium, these are called alkali metals. They're in the same family, the same group. They have similar properties. They all tend to form +1 atoms. To the right of that are the alkaline earth elements. They have +2. Alkaline means basic. So alkaline batteries, if you have an alkaline battery, it has potassium oxide typically in the center, so it's basic rather than acidic. So it's a basic battery. Alkali metals tend to be bases. Alkaline earths tend to be bases, and why are they called earths? Because they tend to be insoluble, meaning they make precipitates when you mix them together. And the alchemists thought that they were forming earth, one of the 4 elements, so they called them alkaline earths. And the middle groups, the transition elements, some of those atoms, elements, they can have multiple charges. So those are not as predictable. And then on the far right, the nonmetals, the fluorine, chlorine, bromine, iodine, those are called halogens. Halogens, it's Greek for salt forming. They make lots of salts. Salts are metals and nonmetals, or another term for salt is the result of an acid-base reaction. Oxygen family tends to form -2 charges. Nitrogen family tends to form -3 charges. So this is the idea behind the periodic table. We can stack it up by properties. So let's talk about the different models of atoms. So let's talk about models. We're going to talk a lot about models. And when I hear the term model, I think of clothing models. I think of the Victoria's Secret models, for instance. I used to work at Victoria's Secret in the corporate offices. And I watched them do this. They would go and they would airbrush the photographs and the models. And the pictures that you see in Victoria's Secret, those are not women. I mean, yes, they are women, they are models, but they airbrush, they make them, they get rid of wrinkles, they get rid of little acne, little imperfections, they smooth edges. So they are actually, no woman can ever look like a Victoria's Secret model, even the models themselves, because they airbrush them to make an ideal. So Bohr came up with a model, and he said that atoms were like, they had shells, they were like onions, or if you like Shrek, ogres are like onions, they're layered. Atoms are layered and they have shells of electrons, and this is the shells, the way the shells worked. And Dalton also explained something when it comes to atoms, that they emit light, and they emit light in specific things. So atoms, they have fingerprints, just like I have fingerprints. Atoms have fingerprints too. My fingerprints, are literally the indentations of the skin in my hand. In atoms, it's the light that comes out. So if I go rob a bank and I leave my fingerprints at the bank, the police can track me down. If we see a specific type of light coming from atoms, we can verify, aha, we found that atom. And let me explain this in a kind of a colloquial example. Imagine a Super Bowl party, okay? And there's a TV, and the TV is like the nucleus of an atom. And in front of the TV, there is a nice, comfy, lazy boy chair. Behind that is a nice, comfy couch. Behind that is hard chairs to sit in, and behind that is standing room. So if you're the first one at the party, what do? Well, you sit in the lazy boy, right? And the next people that come in, they sit in the comfy couch, and then so the different areas, the shells fill in terms of lowest energy. The lowest energy are the ones closest to the television, so you don't have to see. And also, I have the lazy boy because it's the most relaxing place to sit in. What happens when a person gets up to go to the bathroom and leaves the lazy boy? Someone jumps in and fills a seat. So let's talk about that. When the lazy boy comes available, someone will jump down, and when that person sits down, that person will relax. Relax, and energy is released. And then when that person comes back, he's going to say, get out of my chair, and he can force the person out, but that person, it will take energy to force that person from the lazy boy back up to the couch, or back up to standing behind the couch or something. So there's energy. An electron can be ripped from a lower energy level to a higher one, but it takes energy, and then that excited electron can then fall back down. When it falls back down, that's called relaxation. So when you go from standing to sitting in a lazy boy, you relax, and energy is conserved. The energy has to go somewhere. The energy is released in terms of light. So little jumps require a little bit of energy, big jumps require big amounts of energy. And these line spectra here, these are the fingerprints. So looking here, sodium, we see this a lot in Hawaii. We have the sodium vapor lamps. You've probably seen this kind of orange color. You'll see it when you look at lamps. They have sodium vapor lamps. Why do we have that here in Hawaii? Because of the observatory. So the light pollution that way them at the observatory, they can just look at, when they see this color, they know it's from Honolulu and not from some distant galaxy. But here, looking at hydrogen, you can see this line spectra, this fingerprint for hydrogen is different than for calcium here. So these are the fingerprints for them. When you see these lines, that means that you have that specific element present. And the other thing to note, the energy levels are discrete, so they're not continuous, meaning, so you look up here, there's a continuous spectrum. These are all energy levels. Electrons exist only in specific energy levels, so it's sort of like floors in an elevator. You go from first floor to second floor to third floor to fourth floor. So these, actually I guess we'll be backwards here, these correspond to different floors in an elevator, not in between them. And those are the different shells from the Bohr model. And here's another way of looking at it, that the different energy levels, as they relax down, they emit different colors, different energies of light. And our eyes, though, so why don't we see, when we look at hydrogen, it looks kind of pinkish if you look at the spectrum. Why does it look pink? Well, it's because our eyes are not spectrometers. We have simple eyes. We see an average of all the colors put together. And here are the different salts, so lithium, sodium, potassium, calcium, strontium, and this is where you get the colors in fireworks. So fireworks come from the salts. That's what you do. You pack a salt into an explosive charge, the heat from the explosive charge excites the electrons in it, and it releases the colors. That's why when you see enough firework displays, you will see the same colors over and over and over again. And here's the electromagnetic spectrum. And then these do different things. So on the low end of the spectrum, we have radio waves, then we have microwaves, infrared, visible. Then after visible light, we have ionizing radiation, which means it can create ions. We have ultraviolet, X-rays, gamma rays, and cosmic rays, which are even higher energy photons. These do different things. Radio waves, the way radio waves work is they cause the nuclei, the magnetic moment of nuclei, to shift directions. So if you've ever gotten an MRI, it stands for magnetic resonance imaging, you are looking at the way your hydrogen atoms in your body, the magnetic poles of that. And so they look where your hydrogen is, and from that they can tell, oh, this is blood, this is ligament, this is bone, this is muscle tissue. They can tell the different types of tissue by the amount of hydrogen is present. Microwaves, the way microwaves work, when you hit something with microwaves, it causes molecules to rotate. So with this, I'm saying this is a water molecule. You hit it with a microwave, it will rotate the water molecule. And a microwave oven works by rotating. So we didn't talk about temperature. Temperature is average kinetic energy, or specifically average translational kinetic energy. So here, if you have an atom or molecule, it's moving around. This is moving around translationally. So a water molecule, it can move translationally. It can also rotate, and it can vibrate. So microwaves cause them to rotate, and when they collide, the two molecules then fall apart, and they translate the energy into translation energy, thus heating it up. That's the way a microwave oven works. Infrared causes molecules to vibrate, and gases that vibrate are also known as greenhouse gases. So a greenhouse gas is one that absorbs in the infrared spectrum. And the primary greenhouse gas for the Earth is water vapor. There are smaller contributions from carbon dioxide and methane, but the primary one is water. And we'll talk about that a little bit more when we get to the atmosphere. What visible light does is it causes electrons to jump energy levels. And the different colors come from the magnitude of the jumps. Ultraviolet is ionizing radiation, so it creates ions. Ultraviolet light ionizes the electrons at the top. X-rays ionize electrons in the core. So UV ultraviolet light hits the valence electrons, the outside ones. X-rays go for the core. Gamma rays deal with the nuclei, and gamma rays will deal with the nuclei and the nuclear events within the atom. So what do you think? Can cell phones cause cancer? This is in the news quite often. Turns out cell phones cannot cause cancer. It doesn't matter what people say. In modern science, in contemporary science, it's based off of reason and experiment. Cell phones use microwaves. They cause molecules to rotate. In order to cause cancer, chemical bonds need to be broken, specifically chemical bonds in your DNA. Microwaves cannot break chemical bonds, therefore they cannot cause cancer. So no matter what you hear in the news, it's complete rubbish. It's just not true because of physical reasons. So let's go talk about electrons. And there are two types of electrons. There's valence electrons and core electrons. Valence electrons are the outer electrons, and core electrons are the inner electrons. And I'll show you some pictures. The atoms that have 8 electrons tend to be more stable, and these are the noble gases. And the generalization here is the octet rule. Helium only has 2, so you can see it doesn't fit, but things tend to go for 8 electrons. And here I'll show you the chlorine atom. It has 7 valence electrons, outside electrons. It has 2 shells. It has 2 electrons on their 8, so it has 10 core. But the valence, the 7 on the outside, those are the outer, and then the ones in the core. When it gains an electron, it has the similar chemical structure to argon. And we're going to talk about the Lewis dot structures. When you make a Lewis dot structure, you ignore the core and only deal with the valence. So the different groups will have the same number of electrons. And here shows you the first row has just 1. These are the alkali metals. The second row has 2. These are the alkaline earths, and so on. Now, this kind of reminds me when I used to live in Wisconsin. When I lived in Wisconsin in the wintertime, you could not tell the sex of someone because this was also in the 90s when you had the Nirvana grunge era, and basically everyone wore brown coats and faded jeans and brown hats. So that's all you could see. You cannot see what the person was wearing underneath because the outside electrons blocked everything. So chemistry and chemists are very superficial. We only care what's on the outside. So here, oxygen, sulfur, selenium, tellurium, these all have 6 electrons on the outside, and so they're all going to react very similarly. And as you take off the different levels of electrons, you go into the core electrons. You can look at it another way. Hydrogen has 1 electron, 1 valence electron, no core. It's like a guy wearing a pair of board shorts. Just 1 item of clothing, nothing else. Helium is sort of like a girl in a bikini. 2 items of clothing, nothing else. 2 outer electrons. Lithium is kind of like a girl in a bikini with a trench coat. So the trench coat is what you can see on the outside, the 1 valence electron, but you cannot see the bikini underneath. It blocks it, so the 2 core electrons are not visible. They're not really that important. They don't engage in chemical reactions, but the outside clothing or electrons, those are the ones that matter. And the periodic table, the rows, so periodic table, a row in the periodic table is a period. So the periodic table are the rows are periods, and columns are groups or families. And since they all have the same number of valence or outside electrons, their chemistry is similar. Here's a picture of my family. You can see us, we're kind of like a blonde tribe here. There is me, and then my three sisters, my brother, and my parents. So we all, we're each unique and individual, but we look alike. And that's why we're a family. Likewise, a family in the periodic table is going to look and behave similarly. And my family and I do. We all have, we all have blonde hair, kind of a big build, and we all pretty much have the same sense of humor, believe it or not. And as example, copper, silver, and gold. So at first glance you think, well, that's not really, they're not very much alike, though. I mean, they're different colors. Silver is kind of the color that almost every metal is. Gold is kind of yellow, and copper is kind of red. But really, they react very similarly. They're not very reactive, meaning that copper, silver, and gold are not very reactive at all. They're also valuable, and they conduct electricity extremely well. There's similarities, but they're not the same. So here, there's a picture of my dad, my brother, and then my brother's son, all John Ferguson. And so you can see that they have different, they're each are different people or different elements, but they are quite similar, and we group them into families. And just like people, atoms bond with each other, and there's different types of bonding. First type of bonding I'll talk about is ionic bonding. And this is when one atom gives electrons to the other atom. And then after it forms ions, so ionic bonding, and the positive and negative charges attract, but then the negative and the positive similar charges repel. And they organize each other such that they're as close to the opposite charge, but as far away from the like charge as possible. Covalent bonding is the sharing of electrons, and we'll get to polar covalent when there's unequal sharing of electrons. And metallic bonding, so a metal, it's a sea of electrons. It's kind of like a bunch of positive nuclei with electrons flowing between them. Molecules, molecule is a stable group of atoms. So the key word here is stable. Stable means they stay together. So compare a stable couple to an unstable couple. Stable couples are always holding hands, they're kissing, they're hanging out together. An unstable couple, they fight and they split apart. So an unstable molecule will blow up and the atoms will fly apart. A stable molecule will stay together. And metals and nonmetals react, and these produce ionic compounds, and then they form crystalline solids. It's a caution, some of these bonds are strong, some of them are not very strong. Be very careful if you have a tungsten carbide ring. Tungsten carbide is a very durable solid, and they cannot be broken by the jaws of life. So do not wear your tungsten carbide ring if you have one, if you're working on your car, for instance. They will have to take apart the car to get your hand free. They will not be able to cut the ring. And here is an example of reaction. To the left here we have chlorine gas and sodium metal. It reacts to form sodium chloride or common table salt. It's an ionic compound. And we've talked about this before, and I talk about salt. Here is salt, and you see purple sodium atoms and green chlorine atoms. Forms a crystal lattice, or the salt crystal you can see that you're familiar with. And compare this here, this image of a salt crystal. What happens if you just move one of these atoms just a little bit? Well, what happens is that you have a negative ion, too close negative ion, and just with a little whack of a hammer, you can break apart a salt crystal pretty easily. But a metal, if you whack it with a hammer, it just bends, because metals are ductile. Why are metals ductile and ionic bonding, they're fragile? Well, because if you move the atoms around, you have a sea of electrons through it, so they flow just as easily. So this sea of electrons, you can move the atoms around and they still bond very well. That's why you can melt metal and you can form it into new things really easily. And this explains a lot of things. So chemistry is a study of matter and its changes, Now, just by chemical bonding, you've explained why metals behave the way they do and ionic compounds behave the way they do. Let's talk about covalent bonding. Covalent bonding is when electrons are shared. And when two electrons shared, you have a single bond. 4 double bond, 6 triple bond. And these are stable. Remember we talked about that molecules are stable. And why do they do this? Well, they do this as a friends with benefits type relationship. They both, when they join together, they both have a noble gas configuration. So remember, atoms try to be like the noble gases, and they will bond to form noble gas-like relationships. And atoms are kind of like people. Different people are more attractive to the opposite sex. Likewise, different atoms are more attractive to electrons. So electrons really, really like fluorine, but they don't like cesium as much. Why? Because fluorine is a small atom with a really positive nucleus. And cesium is kind of a big, clumsy atom with a really weak positive nucleus. And so because of that, when things bond, they can be blanket hugs. If you've ever shared a bed with someone who is a blanket hug, that person can take all the blankets away from you. Likewise, in a polar covalent bond, one atom will steal all the electrons from the other atom. And the trend is that the further to the right and up the periodic table you go, the more electronegative things are. And this unequal sharing is a polar covalent bond. And here's an example here, kind of like HCl. You can see HCl, hydrogen and chlorine in bed together, but chlorine stealing all the blankets and stealing all the electrons and letting a little corner there in hydrogen. So because of that, there's a really strong negative charge on the chlorine atom and a positive charge on the hydrogen atom. That's the polar covalent. So polar, like a polar bear you find on the North Pole, right? So a polar covalent has two poles, a positive and a negative pole. Then they're free radicals. Maybe you've heard of free radicals. These are species with an odd number of electrons, or unpaired electrons. And these tend to be very reactive. And what they can do is they can create chain reactions. So fire is defined as a rapid oxidation reduction reaction. Fire can be put out by using halon fire extinguishers because they get rid of the chain reaction. Also, sulfur hexafluoride is added to jet fuel. That's part of our stealth technology. It creates free radicals that get rid of the heat signature, and it makes it harder for jets to be tracked on radar due to the electron scavengers we put in the fuel of our fighter jets and our bombers. Now let's talk about shapes. Shapes will define a lot, and in general, the negative electrons are attracted to the positive nucleus, but they're repelled by the other negative electrons. And these form shapes, and I'll go over these shapes. So the first one here is linear. So remember, these two here, the green chlorine, they are really attracted to the beryllium, but they are completely repelled by each other, and they form a line. And actually, if you ever go to a dance club and watch people dance, people react the same way. So if two guys are interested in the same girl, they kind of form a linear sort of sandwich maneuver. And because they're trying to say, I'm attracted to you, the female, but I find this other man extremely repulsive, so they try and be as close to the female and as far away from the male as possible. Likewise, if three men are interested in the same girl, they'll kind of form a triangle pose so that they will be as close to the opposite, but as far away from the same as possible. Now, after 4 atoms, this analogy breaks down because with 3 dimensions, 3 can crouch down and then 1 can stand on the head. This is a tetrahedral. And then if one of these atoms is an electron group, as a lone pair, you can get the pyramid and then the bent structure. And then this is also a bent structure. And let's talk about how to name things. So it's easy with 2 elements. You give the first full name and then the root of the second way name plus IDE. Sodium chloride, iron bromide, nitrogen oxide. But with Iron, bromide, nitrogen oxide, we have to talk about these later. Iron, you have to give the charge, iron 3 bromine, and nitrogen oxide, you have to say dinitrogen tetraoxide. But we'll start with the simple one, sodium chloride. Now, with other metal, non-metal compounds, some of them only have one charge, like sodium chloride. Sodium is always +1, chloride is always -1. But iron can be +2 or +3, so you have to state that. And either you say it or you give Roman numerals. So this is iron 3 chloride or iron III. Well, you won't say III, you say iron 3 chloride, and you write it using the Roman numerals if there's more than one charge. And now for other things, you can use the different numbers. So for the numbers, I'll show the next one. If the first atom has only one, you drop the mono. But if there's more than one, you have to include the next of them, and then you put the different prefixes. So this is sulfur trioxide, you drop the mono. N2O4 is dinitrogen tetraoxide. And here are the different prefixes. So mono is 1, di is 2, tri is 3, and so on. And then polyatomic ion, so a monatomic ion. When you're in a monogamous relationship, you see one person. A polygamous sees 2 or more people. So polyatomic means many atom ions. So you have a group of atoms, and they link together, and they share a charge. And so here are some common ones here. And here are some common compounds. Ammonium nitrate, this is a fertilizer. It's also an explosive. Calcium carbonate, this is coral limestone. Ammonium hydroxide, this is found in many cleaners. Ammonium phosphate, also a fertilizer. And then ending here, electrolytes. Certain compounds, when you dissolve in water, will completely break apart, and they will be able to conduct electricity. So if you drink certain sport drinks, they say that there are electrolytes in them. What does it mean, electrolytes? It means they have sodium or potassium salts, more often sodium salts, because the sports drink can now conduct electricity, and you need electrolytes in your bloodstream. So these types of solutions, sodium chloride, hydrochloric acid, and sodium hydroxide, these break apart, and then now they conduct electricity. Pure water does not conduct electricity very well. So you have to add something to it to make it conduct electricity. And here is the end of our second lesson. I will see you for the third lesson.